I love the camera. Just makes me start right on time and only a little bit late. Here's our public service announcement for the exam. It's coming up. It's 2 weeks and 2 days away from now. We have 3 more lectures to go, and then it's exam week. The 3 lectures are all going to be about noise. And today, we're going to start talking about noise in analog systems. Last time we looked at noise in the detection of digital signals. This time we're going to look at it. We're going to go back to AM, and we probably won't get to FM today, but we'll try, and put noise in those systems. I like doing this at the end of the class because it's been a long time since we looked at AM systems, and it's been a fairly long time since we looked at FM systems. So in today's lecture and Monday's lecture, those will be good reviews. They'll be reviews with a little bit of a twist, and the twist is the addition of a noise, of a noise term in the whole system approach. And then if we have time on next Wednesday, I want to talk a little bit more deeply about a particular type of noise and where it comes from, and that'll give you an idea of the statistical approach to understanding noise. Okay, we looked at that a little bit last time, right? From a high level, the voltages that registered a 1 varied all over the map, and that gave us a distribution. The voltages for 0 also varied all over the distribution, and so we reminded ourselves of probability and statistics, of Gaussians, and the error functions that went with the Gaussians, and we used those formulas to come up with a measure of performance, which was the bit error rate. Okay, so we're going to look at similar figures of merit for analog systems. Okay, in today's class and in Monday's class. Now, how to start this? I think the first thing I want to point out is something about my message signal, M of t. And one of the things that I've mentioned, and probably not often enough, but one of the characteristics about an information-rich message signal is that it's very random. I don't know if you remember me standing up here and saying blue, 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 blue. That's a very boring message signal because you know that the next word out of my mouth is also going to be blue. Right? So that message has a lot of repetition. It's a very regular message. And therefore, by that very nature, by the statistics of it, it carries very, very little information. And so for M of t to be very information rich, it appears to be random. Okay? So the message signal appears to be random. That implies that it has lots of information. Okay? Now, you've all heard noise. You've all heard static. You've all heard, garble. And so, if I write down an N of t, and I say there's not a lot of information in there, well, you'll agree with that. But it's remarkably similar to M of t in that it is random. The voltages, as a function of time, are just as random as M of t. Okay? And it's very hard, given the random process nature of both M of t and N of t, it's very hard to work with those in the time domain. And so our answer is, for M of t, what we say is, yes, we don't know the precise trajectory of M of t in time, of the voltage M of t in time, but we do know something about the statistics of it in the frequency space. And one of the things that we've always said is that it has some distribution and is bounded into a certain bandwidth. And so when we've had to do design, spec filters and so on and so forth, calculate the bandwidth of an FM signal, we've always had something to say about the frequency dependence of M of omega on average, even though we've had very little to say about what M of t specifically was. So in other words, a telephone conversation that you might have to your significant other, to your mother, or your stockbroker, will have very, very, very different M of t's, but they'll all fit the M of omega statistics on average. And so when we design our link according to M of omega, the statistics of M of omega, then we don't really care. Our communication system doesn't really care if you're talking to your brother or your boyfriend or your stockbroker or your boss or what have you. Okay? Because so that's one of the things that we've talked about, but I want to emphasize now with respect to this noise, N of t. N of t is random. But the fact that we have said that we're interested in an M of omega over a certain bandwidth range allows us to manipulate what N of t is through a variety of these techniques that we've developed. So what we care about is N of omega for the same reason that we care about M of omega. We will pretend we know something about the statistics of N of omega in the frequency domain, even though we know nothing about what the next level of noise is going to be out of my resistor or out of my detector. Okay? We only know on average what it's going to be, and on average leads to a certain frequency distribution that we can work with. Okay? All right. Now, I've written this N of omega as a script N of omega. And that's because the units of this is the spectral density. It's going to be watts per hertz. So it's going to be spectral density by which we characterize different noise. For example, there may be Gaussian noise, in which case if I plot the spectral density as a function of omega, I'll get a Gaussian. The variation in the frequency space of any particular level of watts at any given hertz is going to be shaped like a Gaussian. So one way to think about that is if I have a 1 hertz sliver, then inside that 1 hertz is going to be a certain amount of watts. If I have a 10 hertz sliver, then the total amount of watts that's found in that 10 hertz sliver of bandwidth is the area under that curve. Okay? And so what we would do is we would say the total amount of power will equal to the integral of the spectral density across some bandwidth delta omega. And for a Gaussian, that's a difficult integral to do. It's the difference between two error functions or two complementary error functions. Okay? And so you have to program that into Excel to do that, or look it up in a table of those integrals. Okay? Like we did last time, a little bit. Okay? So the script n of omega is going to be a spectral density, watts per hertz. And to calculate the total noise power, the total amount of noise power, I'm going to integrate that across the bandwidth that I'm interested in. And now you understand why we ask questions like, what's the bandwidth of an AM system? What's the bandwidth of an FM system? Because that's the bandwidth that we're interested in for filters. And those filters are going to are also going to filter out noise. So if I have a bandwidth, a bandpass filter, that lets in just an FM signal and nothing on the wings, then no noise from the wings are going to come in, but noise inside that window, filter window, will come in, and it will pollute my signal. Last time we came up with a gamma, M1 minus M0 over sigma 1 plus sigma 0. In terms of voltage, that's the voltage signal divided by the voltage noise, or the voltage uncertainty. Today, in the next class, we're going to be mostly interested in signal-to-noise ratios that are power-based. Okay? So in today's class, we're going to look at signal-to-noise ratio, which will be the signal power divided by the noise power. Okay? So it's the power of the signal divided by the power of the noise. So that's going to be our figure of merit for what we're going to do. Okay? Now, I want to talk a little bit more. There's other distributions, and in fact, most of what we're going to be doing will be very, very simple distributions. But I want to talk a little bit about what kinds of distributions that you might see out there. Okay? Do you remember the black body curve? Never mind. One interesting observation that's made is that if I look at noise in the universe as a function of frequency, and I'll write for once frequency in hertz, not radians per second. It doesn't really matter for this. Okay? It turns out that the higher the frequency I go and look at, the lower the noise. The higher the frequency that I go look at, the lower the noise. Okay? And that kind of makes sense because higher frequencies suggest higher quanta of energy. And if I don't run out of the population of that, then I'll have an unbounded power or unbounded energies. So there's something about conservation of energy that makes that kind of nice. But from a pure empirical perspective, the shape of this curve is that as you go higher and this is the noise spectral density, again in watts per hertz, and I'm plotting this as a function of hertz, the roll-off here is 1 over f. So if I go increase my frequency by an order of magnitude, I decrease my amount of spectral density of my noise by an order of magnitude. Okay? So my 1 over f noise is pervasive in many systems, and a variety of these systems have been independently have had theory to independently justify this 1 over f. But there's a very deep and rich question is, why is most noise out there behave to a 1 over f? Okay? This is just a very interesting point. Now, at the risk of getting ahead of myself, we talked early on about the why we would want to modulate a signal, why we would want a carrier. And one answer I gave you was the electromagnetics of a gigahertz signal is very different than the electromagnetics of a 1 hertz or a 10 hertz signal. Think of the antenna size that you need to build a 10 hertz system versus a gigahertz system. Right? Wildly different geometries. One trivial to carry in your pocket, the other very difficult to fit into the state of Texas. Okay? So another reason why we want a carrier frequency is because we move from baseband out 6 to 9 orders of magnitude. Which means 1 over 10 to the 6th, 1 over 10 to the 9th, we drop way, way, way down in noise. Okay? But if I'm at baseband, bad example. If I'm at some carrier out here, and I look at a gigahertz, which is a huge spectrum, right? Gigahertz around a gigahertz, well, a gigahertz around 10 gigahertz, okay? Or 100 megahertz around 1 gigahertz, 10%. That's a huge spectrum, but if I draw it on this graph, it looks like that. And if I'm kind of a sloppy engineer, and I want a good answer, I can just draw a line there. Okay? And so for our examples, what we're going to say is we're going to have a constant level of spectral density, noise spectral density. A constant level of watts per hertz in the region of interest. In the region of interest. Okay? And this is called, I call this flat top noise. It's also because all frequencies are treated the same, have the same strength. It's also called white noise. So those are terms of art that are found in the literature. Well, basically what it means is when I go back to calculating my noise power, n of omega is the integral of the spectral density. This will equal n of omega, because this is just a constant, right? So I can just pull that through the integral. And then when I integrate this constant d omega, I'm just left with the area under the curve. Is just that little rectangle there. The width, delta omega, multiplied by the height, n of omega. So my noise will be the spectral density multiplied by the width of my window. So the broader my bandwidth is, the more bandwidth I use in my spectrum, the more noise I let into my system, the more noise I let into my integral. So do you remember when we were talking about single sideband versus double sideband? Well, double sideband is wasteful for a variety of reasons. And now we see that it's wasteful because it lets twice the noise in our system than we need. We can, if we build our filters to be half the bandwidth, we let in half the noise, which means we can go much further on our link distance. Okay? And so that's a good thing. So we see instantly, we see right from the very beginning, before we've even touched AM or FM or anything like that, we see a couple of truths about how to deal with noise in this system, in these systems, which is narrow band filtering. Really narrow band filtering. Okay? The tighter the filter is, the narrower this window becomes. Okay? I also want you to start thinking about something that will seem like no big deal at first, and then as you start to think about it, it's going to blow your mind. But if I have this distribution, this n of omega that's flat, okay, and I say I have a gigahertz signal and I've got a delta omega of 100 megahertz. That's pretty much what I've drawn there, right? Well, now let me say that supposing I have a gigahertz signal and I bring the 100 megahertz down to 10 megahertz. And then I bring it down to 1 megahertz. And then I bring it down to 0.1 megahertz or 100 kilohertz. 10 kilohertz. 1 kilohertz. Okay? I start to get something that doesn't look like noise anymore. I start to look like a sine wave again. Okay? Now there's some random properties to the sine wave, but it's not necessarily. There's a lot of parallels with that. In other words, it's a sine wave that's been muddied up, scrambled up a little bit. It's nominally a 1 gigahertz sine wave to 1 part in 10 to the third. Pretty good quality factor. It's not a perfect sine wave, but heck, the message signal is not a perfect sine wave. So a lot of the forms that I use to describe a highly filtered noise term will be very similar to a message signal based around a certain carrier. The math that we will develop will look very similar. And it doesn't seem like a big deal now, but when I start writing those down, it's like I said, you're going to get very uncomfortable. So I want you to start thinking about that. I want you to start thinking about what it means to have a signal, in particular a message signal, that occupies some fraction of a bandwidth around a carrier. And what happens if I replace that signal with a noise? Okay? Two sides of the same coin because of the random processes going on. All right? So that just should prime the pump a little bit for that. Okay? Now, let's go back to our basic link. And I start with an input M of t. And I go to some transmitter. Okay. We'll do the AM case. We'll do a baseband case. We'll do the AM case. We'll do phase modulation. We'll do frequency modulation. Okay. We'll do the examples of the analog systems that we've studied. Review. We'll transmit a certain power, ST. We'll transmit a certain power, ST. Could be 10, 100 megawatts out of a commercial radio station, for example. We'll go through a channel. And now, because it's very important to the problem, the attenuate, we'll talk about an attenuation. And this attenuation can be huge. When I teach fields and waves, one of the things I think about is I tell you to think about is take a balloon, okay, and the balloon, I'm imagining this balloon sort of fitting over an antenna, okay, and so this balloon or this net captures the amount of power that's emitted from this antenna, okay, and so if I have a cell phone, the balloon is kind of the size of my, I don't know, what is that, a cantaloupe or so? How big is that? Cantaloupe. Okay. So that's about the size of the net or the balloon over this antenna that captures, and it's wholly around the antenna, so it captures all the power that leaves the antenna, and it crosses it. In EMAG, that's the Poynting vector, integrated across the solid radians, the steradius. Solid angles at a particular. Okay. So what I want to do is I'm going to imagine that power as peanut butter, and so I'm going to coat the balloon with a layer of peanut butter, and it'll be a lot of peanut butter. So I'm going to put on maybe an inch of peanut butter or a quarter inch of peanut butter. So next time you're at the supermarket, imagine a cantaloupe and a jar of Jif peanut butter, and you smear a quarter inch of that. Okay. Well, now your base station for this might be a kilometer away, and so all of a sudden the radius of that cantaloupe has gone to a kilometer. So from 10 centimeters or for 0.1 meters to 1,000 meters, and I smeared a quarter inch or an inch of peanut butter on that thing, but how thin is that now? Right? It's tiny. It's a minuscule layer. That's really the attenuation problem here. That decrease in the thickness of that peanut butter is the attenuation problem here. And so the surface area can go as r squared. 0.1 meter to a kilometer is 4 orders of magnitude in radius, which is 8 orders of magnitude in reduction in size of that peanut butter thickness. So your attenuation could easily be 10 to the 6th to 10 to the 8th. Very, 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 very severe attenuation. And I haven't even talked about the absorption of the building materials for this poor signal that has to transverse walls. Okay? I don't know if you get a sense of that in your EMAG course. But, the peanut butter analogy just really does it for me. Hope nobody's allergic to peanuts. So, I've beaten up my signal 1,000,000 times or 1,000,000,000 times in terms of amplitude. Okay? And at this point, it's really weak. It's a really weak signal. And I'm going to say that this is the signal into my receiver. Okay? This is the place where noise will strike. This is the place where noise will strike. Now, in practice, noise will happen everywhere along this line, right? Random processes will flow everywhere inside of this. But when we model it, we model an additive noise source right at the receiving end. So input into my receiver will now be a power level that's associated with my input signal and a power level associated with my noise. Okay? That's my signal to noise ratio on the input to my receiver. There's also a signal to noise on my output. Filtering, coherent detection, those are tricks that can be used, as we've seen, to start to winnow down some of that noise. But I hate to say it, it's a pretty hopeless task. We're not going to be able to, because the noise looks so much like the signal, that I have to have a pretty good way it has to be pretty obvious why they're going to be different. For example, outside the skirts of a bandpass filter, that noise goes away. But if I'm interested in that frequency range for my message signal, M of omega, then I can't tell the randomness of the noise from the randomness of my message signal. They're too intertwined. And so I will always be left with some ratio of S out over N out, which is my signal to noise ratio. And as we saw last time for the simple digital case, the more noise there is, the less my signal to noise ratio will be. And the more mistakes and the more garbled it's going to be. Or conversely, the lower my signal level is for a given amount of noise, the more my performance of my system is going to be degraded. So it doesn't matter what my signal level is. It doesn't matter what my noise level is. What matters is the ratio. If everyone's quiet in this room, I can get away with a whisper. If you all start talking and rustling your papers, then I yell. But in either case, my goal is to achieve the same SNR, signal to noise ratio. Okay? So if there's more noise, I have no choice but to raise my signal level. Okay? That's an unfortunate fact of life. Now, since I'm interested in the signal to noise ratio, there's really two pieces of this. There's going to be the calculation of the noise level, and for all intents and purposes, that's really going to be an integral across some bandwidth times the noise spectral density, which will really boil down to some amount of noise times bandwidth, W. Because in the examples that I'll give in the classroom, we're going to assume a flat top noise distribution, a flat top noise spectral density, a narrow band noise source with which it might as well be constant anyway. Since you've got me on that topic, I might as well draw a slope that looks like this, and a delta omega that I'm interested in, or a W, a width of my window. And I say, okay, I want to know my signal to noise ratio. And I'm interested in all frequency components equally. Right? I'm interested in all frequency components equally. Does it make sense to talk about the lowest level of the highest level of signal to noise, the average level of signal to noise, or the worst case level of signal to noise? And if we really care about all frequencies, there's an argument for considering the worst case noise anyway. Okay? That's a detail that's your mileage may vary on, but it's an argument that comes up from time to time and is not an invalid argument when you actually roll up your sleeves to do an engineering design for a commercial system. For example, In today's fiber optic systems, you might have 80 different wavelengths, 80 different lasers across 30 nanometers of bandwidth. And the customer doesn't know which laser he's going to be transmitting on. He just cares that he has a certain level of performance. And so what you do is you spec the signal-to-noise ratio for that system, the optical signal-to-noise ratio for the system, as the worst channel, the channel that sees the most amount of noise and suffers the worst amount of degradation in the channel. Okay? So it's not a typical channel, or it's not the average channel, or it's not the best channel that makes it through. It's what's the worst performance that any of your customers are going to face. So that's the weak. The group is only as good as the weakest channel, right? The chain is only as good as the weakest link. Well, the same principle here. Okay. All right. Now, so that's that. And then the other thing is we need to know something about S in and S out. Okay. So that there's not a lot of ways that we're going to really be able to frame that. So a lot of these formulas are going to be fairly simple and simplistic even, but they'll give us a perspective. So consider a baseband system. And what I mean by a baseband system is I'm broadcasting at 100 hertz. So I have a music generator, and I'm just going down a transmission line at 100, like it was an electrical signal. Okay? Or I have anyway, okay, so my noise will equal and I'm going to have a certain window associated with it. So my noise power will be N naught times W. My message signal will give me a power or it will equal the integral of m of omega, and I'll just label this equal to S out. And so for a baseband system, my SNR is equal to S out over N out times the bandwidth of the system. And this is I think in Latin he calls that a gamma. Okay. Now let me just take that formula, go back to this equation here, or back to this picture here, and do a quick example. So I have this message signal that has a bandwidth of 5 kilohertz. Okay. I have a noise spectral density of 10 to the minus 14 watts per hertz. Channel attenuation is 10 to the minus 12. I want my output SNR to equal 6 dB. What's my launch power, ST? So, one formula that I know is S out over N out, which will equal the launch power, ST, times my attenuation, and that's my power that's received from my signal. The noise power is 10 to the minus 14 watts per hertz, integrated across a 5 kilohertz window. So that's 10 to the minus 14 times 5,000. And that has to give me 6 dB of signal to noise. Okay. So 6 dB is equal to 10 times the log of P out over P noise. 10 because it's power, right? And that has to equal 4. Okay? So you have to go 10 to the 4th, and that's your ratio. You put that in, multiply by 500, multiply by 500, multiply by 10 to the 14th, divide by 10 to the minus 9, and I'm sorry, that should be implied there. So, yeah. So 6 dB, 10 log, power out over power noise, that has to equal 4. That implies a linear ratio of 4. One way that I think of that, by the way, is that it's 3 dB for every factor of 2. So 6 as a 3 dB, that's one factor of 2. And another 3 dB is another factor of 2. 2 times 2 is 4. Okay? 10 dB is an order of magnitude. Okay? So if this were 10 dB instead of 6 dB, then this would just be 10. Okay? So that's how I get my way around. That's how I work my way around dBs. It's 3 is a factor of 2. So 3 and 3 and 3 is 9. That's 3 factors of 2. Or 24 dB is 2 factors of 10, and 1 factor of, or 24 dB is 2 factors of 10. That's 20. And then another 3 dB. So that's 20. It's 40, factor 40, and then I have another 1 dB left over, which is a little bit more than that. Okay? Gets me up to about maybe 50, 45, 50 dB, 45, 50 range. Okay? So that's sort of a fast shorthand way around the dB scale that kind of helps you out. Anyway, I know you just want the answer here. ST is, although in that dialogue you should have, or monologue, you should have been able to calculate it. 10 to the minus 12, and I got 200 watts, and I would encourage you to double check that and make sure my math is okay. All right. So you have to launch 200 watts to get that, to overcome that. In that fictitious made-up example. All right, so now that was at baseband. Now I'm going to do an AM system. So M of t comes in. I've got a local oscillator. Mix it. I go through my channel. I add noise. I've drawn a bandpass filter here. Before I didn't really need it, but now with the addition of noise, I kind of do. And so this bandpass filter is going to be centered at the carrier frequency, and it's going to have a bandwidth capital B to let through my signal. And it eliminates whatever noise is outside of my bandwidth of my bandwidth of interest. Okay? So this is my windowing function, and I put this component in there because what I want, this noise is flat-topped. It has noise at all frequencies. My signal only has noise at particular frequencies. So why should I pay the penalty of noise that's outside my region of interest? So this bandpass filter in communication systems is huge. Okay, it's a huge design parameter, and we didn't really need it before. Before, if we had it in there, it didn't affect anything, but we didn't really need it. Now it's serving a real function. It's getting rid of noise that's going to creep in and pollute my signal. Okay. Just to digress, the realization and control of that filter is really. It can be quite sophisticated. For example, you might imagine in some architectures, you might imagine being able to control the 3 dB bandwidth of that filter. You might be able to control the skirts, how the DSP of that. Well, in optics, that's almost you have to do all this in the optics frequency, in the optics range, and so you might control the position by a tilt or by a tilt of a piece of glass that's been coated, okay, or sliding it over, and so what will happen is you could actually be making a measurement of your bit error rate in an optical system and feed back and adaptively control some of the filter characteristics. So if your signal wanders over, your filter can slide over to catch it, and so you don't need fixed guard bands. Okay, so there's a lot of tricks that can be played by intelligent engineering of that bandpass filter, particularly with a feedback loop to control it, so that you're not wasteful. You're not opening your window too wide. Supposing your carrier frequency wanders around, or your message signal frequency breathes in and out. You don't set a fixed filter to the worst case. What you do is you adapt your filter so that only the frequencies of interest come in. Okay. All right. I'm going to describe this as S in, N in, and the signal will be, I'll label Y of t there. Okay? And the output signal here will be Y out of t, and it will have a signal out power and a noise out power. And what we want to do is we want to analyze the system so that we understand what Y input of t is, Y output of t. But most importantly, we understand what the signal-to-noise ratio is on the output. Yes?
Is the addition of the noise term in the block diagram, summation, does that have to do with the type of modulation or the type of noise involved?
So the question is, the precise nature of the summation. Is there anything about that that's dependent on whether I have an AM system or an FM system or anything like that? And the answer is no. Well, the premise is purely that I've got some waveform here, and I choose this point to add in an additive noise term on top of it. Okay, so the signal itself does not affect the level of noise. But I'm doing it after the channel where the attenuation is the worst, because that's going to be the worst case. That's when you think about it. When the traveler is really tired, that's when the wolves come out and pounce. Okay. If the noise attacked the traveler when he was really fresh, the wolf would be toast. But once it's really tired and about to, I don't know if you experienced that walking across the parking lots. I'm going to throw in a few Lottie terms here. The square root of 2, you can recognize that from the good theorist that Lottie is. And similarly here. And that makes my problem pretty much complete, I think, in what we want to do. So, to calculate what this y input of t is, I draw upon some of the lessons that we've had before. M of t multiplied by this term here will give me a square root of 2 times m of t times the cosine of omega ct. That's the signal right there. The channel will assume does nothing for now. Okay? If there's an attenuation, that just changes that value of the square root of 2. Okay? So n of t gets added on. And so that's explicitly, Brian, that's explicitly what I mean by what that summation is. Whatever comes out of my channel, you add on a noise term on that. Okay? So that makes it explicit what operation I'm doing with that guy. Okay? Now what's nice about this, and not to be taken for granted, okay, is that this guy here is SI of t. Okay? And this guy here is clearly labeled noise of t. But I'll tell you, if I'm sitting here with a voltage probe, and I put my voltage probe here, and I display it on the oscilloscope, can I look, just by looking at the oscilloscope, can I separate out this from this? Not really. Not really. Unless there's a frequency difference, unless there's something different, fundamentally or characteristically different from the noise to the signal, there's not much I can do about that. I can run a test signal through. If I know what I'm launching, I can run a test signal through. But in a typical communication channel, I can't. Okay? So this is kind of one of the interesting things about signal to noise analysis is sometimes when you're working through it on paper, you can see exactly what term is your signal and exactly what term is your noise. But when you get into the laboratory or you get into the field, you may or may not be able to distinguish the noise from the signal just by looking at it. Okay? And certainly at the signal to noise levels of interest, you can't. Well, remember we want the signal power, and there's not much we are going to be doing about that. All this filtering, all this stuff that goes on through here is designed not to change the signal. This is a perfect restoration. So what I'm just doing is I'm just going to take the average of that for my power, and I'm just going to label that m squared of t, and that's going to equal S out in watts. Okay? So there's not too much I can do with that. As long as I have a perfect receiver, I'm not going to take a hit. I'm not going to lose any of my power. Okay? The noise is more interesting. The noise term goes through a bandpass filter. And when it goes through a bandpass filter, centered at the carrier frequency, after the bandpass filter, my noise of T will be modulated within a bandwidth B at the center frequency of omega C. Okay? So this is what I was talking about earlier. I have a flat top noise, and I start putting a bandpass filter around it. So if let's consider a light bulb. Okay, I have a light bulb, and these light bulbs will emit, into the UV and also into the IR. Our eye doesn't let those pass, and so it sees a response from say 400 nanometers out to say 700 nanometers. 650 nanometers. Okay? And so that's the white light visible spectrum. If I now start taking, say, a gel fill, if I hold up your Vita water bottle, which has a nice pink hue to it, and I hold that up to the light, that pink filter will let more of the red through and will cut off some of the blues. And so again, it'll be further, the spectrum will be further diminished. Okay? If you think about that, that's an uncertain signal modulated around a certain frequency band. And that's exactly what I'm writing here. Okay? The other way to look at this is, do you remember how noise and the message signal were two sides of the same coin? And so what should come through this bandpass filter should look very much alike. Okay? It's going to and so the message signal is the message signal multiplied by cosine omega CT. The noise filter is the noise multiplied by the cosine omega CT. But it also has some phase. It also has things that are random in phase. So part of your signal is going to be multiplied by cosine omega CT, and part of your noise signal, part of your noise is going to be multiplied by sine of omega CT. Now, just for grins, can I ask you, what's the relative amount of this guy versus this guy? Which is bigger? Is the cosine, is n sub c of t, the amount of noise that's in phase with the signal, in phase with the local oscillator? Is that more or less than the amount that's out of phase with the local oscillators? What do you say?
I would imagine less.
Okay, so NC is less. This is the noise. This is the noise term, right? N of t. The amount of noise that's in phase with the local oscillator is going to be less than the amount of noise that's perfectly out of phase with the local oscillator.
That's my guess.
Yeah, the opposite. You say over here.
You say the opposite? You say there's more that's going to be out of phase, in phase, that's out of phase. Well, let me ask you a question. Does the noise know anything about the local oscillator? It knows nothing about the local oscillator whatsoever. So how on earth does it know to dance with the in phase part or dance with the out of phase part?
I imagine it doesn't.
So
my imagining was if any noise that's in the signal will get built into the message signal.
But again, the way I'm modeling the noise, and there's, you may be right that the message signal and the noise signal are related, but they're not in this case.
Okay.
I'm just purely adding them in and they have no knowledge of each other, and therefore no knowledge of the local oscillator. And so from there we can conclude that the amount of this term is the same as this term in magnitude. Okay? So the in-phase noise and the out-of-phase noise. But out-of-phase and in-phase is not confusing enough. And so we call this quadrature. And we like that very much because that loses the lay audience. Okay, it's one of those buzzwords, those term of arts that date back way, way, way back. And we like it very much because it makes us sound like we know something. Okay? So in phase and quadrature instead of in phase and out of phase. And then that'll get you into the club. Okay? But it you know. All right. So we have noise. The bandpass filter makes us look like a modulated signal, like an amplitude modulated. But we have the extra randomness of phase. Oh, by the way, I could also write this as n of t cosine of omega ct plus some theta, right? And I just don't know what theta is. Theta is bouncing all over the place. And so if I use my trig identity here, I come up with this guy here. Okay? Now we see some of the beauty of this local oscillator here. If I take this noise term and I go through the mixer, what happens to the quadrature term? What happens to the sine term?
So by orthogonality it goes to 0.
By orthogonality it goes to 0. Exactly right. After I filter it, and you've done that. We've done that a lot with the single sideband, or rather the QAM. So that sine wave goes away. So that'll be rejected in the local oscillator and the receiver. I'll characterize NC multiplied by my bandwidth. What did I use? Capital B before? And that will be my noise out of my system. Is the amount of power, this power spectral density, in phase with my message signal, multiplied by the bandwidth B that defines how much wiggling I am. And so my SNR will equal S out over NC times B. And that's very similar. Whoops, that should be a script. N. And that's very similar to what I had at baseband. Right? Same form. The output signal divided by the noise multiplied by the bandwidth. Okay? Now, I think that Lati says that this is the same formula. This is the same formula as we get at baseband, right? When you read this in the book, I think he makes some statement that this is the same formula from baseband, and that's sort of trivializing it a little bit, because there's two huge departures from this guy versus this guy. Well, one huge and one not so huge. Okay. The huge one is that the amount in n sub c is going to be much, much, much less than at baseband because of the tendency of 1 over F noise. So the power spectral density, the flat level of my noise is going to be much, much, much lower at the high frequencies of the modulation. That's one of the reasons why we modulate. So this denominator is going to be much lower, which means the SNR is going to be much higher. Okay? Secondly, and this is a small correction, but, well, I don't know, I'll let you decide if it's small or not. This is both in phase and out of phase noise, because there's no reference to phase, because there's no reference to the carrier. But this n sub c is exactly half the noise that entered into my system, because I used coherent detection. Because of that, local oscillator is able to distinguish the in phase from the quadrature. I get an extra 3 dB, factor of 2, an extra 3 dB of my signal-to-noise ratio from that. And as I pointed out last class, most designers would give anything. Most link designers would give anything for an extra 3 dB. I mean, they're poor mothers. Well, never mind. Their lunch. They'd sell their lunch for 3 dB. Okay? All right. Now, one more twist. Suppose the demodulator oscillator is slightly out of phase from the transmitter oscillator. Okay? So if I go back to my system here, this term here has an additional omega CT plus some phase factor associated with that. Okay? So my Y out of T will equal the square root of 2 times the message signal times cosine of omega CT, that's my message signal that's received, mixed with my local oscillator, which is now omega CT plus some detuned angle, phi, and then the noise gets shifted over in phase as well. After mixing, I have that. These are my terms at baseband, and these are my terms at the harmonics. And as we've done a million times, the low-pass filter will take care of those terms. Okay? Again, I'm going a little deeper, a little bit more review. So, my signal level, again, that's nice. My signal level comes out of that term. Cosine squared the signal out drops by cosine squared, which is approximately 1 minus the phase angle squared. So the more detuned I am, the bigger this term is, the lower my output signal is. NC also goes down by the same amount. But now NS leaks in by a sine squared sine of theta is approximately theta, squared is approximately theta squared. And so my SNR prime will equal SNR times 1 minus phi squared, and the denominator will be the same. So what happens is the signal, which is in phase, is discriminated against by the mismatch phase. And so it loses its power. The in-phase part of the noise also drops, but is replaced by the out-of-phase noise, which is now more and more and more in phase. And so the signal-to-noise ratio drops, but maybe not as bad as you think.
On your last slide, what was the signal? The starting signal? Oh, it was Y out. Okay. I didn't see the Y out part.
Yeah, the Y out was all, yeah, think about that. Yeah, you should, yeah, I'll leave this up because it's complicated. I'm intending this as a bit of a review with the extra twist of noise in there. So what I'm hoping is that even though, you know, you've forgotten just a little bit of this, the noise is enough to keep it interesting. You know, and then you learn a little bit more. So we're going to take it a little bit further. Okay? All right. So, next time we'll do angle modulated systems. Okay? So I think this is in 12.3. Is noise in AM and FM signals at chapter 12? I think it is. And so I just did 12.1 and 12.2 today. And so next time we'll do 12.3, which is angle modulated systems. Okay?